Alrighty. So we are now headed into 2 chapters in a row that are a little tricky. Like they're the 2 hardest chapters of the year. Chapter 8 and Chapter 9 are the 2 hardest. Okay, so just to warn you, these are weird and not easy. And that's normal. Okay, but we're going to start with inverses because we're going to be working with inverses a little bit, and that's the whole reason what we're going to be doing exists is inverses. So, first thing we're going to do is we're going to remember how to take an inverse. What do we do to get the inverse? Switch the x and y. So I'm going to come in here and I'm going to find the letter y and I'm going to find the letter x, and we're going to make them change places. So we have x equals 3y plus 1. That is the step that makes the inverse. This is just no longer good math grammar because we don't like to have x equals, we like to have y equals. So what do I do to fix this, to make it look better? How do I get this to be a y equals? How do I get y by itself? Minus 1. So we have x minus 1 equals 3y. I still want to get that y by himself, so what do we do? Because this is 3y, not a 1. I can't push this into here. But I heard this a second ago. We got to divide this side by 3 and this side by 3. So our inverse function is, and we can just leave it as this gross fraction. It's okay. X minus 1 over 3. That's our inverse. And when we look at them really closely, we can see some relationship. This started with a 3x, and this winds up with x divided by 3. 3 times x, 3 divided by x, or x divided by 3. Multiplication and division are inverse operations. They undo each other. On the right-hand side, we're going to do a very similar thing. We're going to start with switching the letters x and y. This is the step that makes the inverse. We switch the x and the y. So we have x equals y squared minus 2. It's now the inverse function. It's just really bad math grammar. What do we do to get y by itself over here? Super close. Plus 2. Because again, addition and subtraction are inverse operations. They undo each other. So we have x plus 2 equals y squared. I still don't want to have y squared. I just want y. So how do we unsquare the y? Square root. So we're going to take the square root of both sides. So our inverse function is square root of x plus 2. So we saw a couple of inverse operations here. It was that we had addition and subtraction undo each other. Squares and square roots undo each other. Multiplication and division undo each other. So what we're going to be looking at today and for the rest of this chapter is an inverse. And by definition, it's an inverse operation. Because if we think about what we had been working on with the last chapter, if I think about if I had y equals 2 to the x, and we wanted to find our inverse operation, we could switch this to be x equals 2 to the y, but at that point we're stuck because we don't have any way to get the y out of the exponent. So what we're going to be working with this whole next chapter is literally a mathematical concept invented to do this. It is the inverse of these. It is why we started the semester with inverses, and we just did these. Now we're going to play with inverses of these. Okay, and it has a really, really weird name, and we're going to get into it. It's going to put a giant wall of text up. It's a clip from the book. Just saying. So this is the graph of 2 to the x. They just did it all weird here. And we're looking at the inverse of 2 to the x. And this paragraph says kind of what I was just saying. When we're trying to find the inverse of an exponential, if I look at 2 to the x and I try and find the inverse of it, we don't have any way to take that y out of my exponent. So in about the 1600s, they created what's called the logarithm. And it's up here. It's spelled weird. Bless you. Called the logarithm. It is the inverse operation of raising something to an exponent. And it's really important that you at least write down the word logarithm and this pair of statements. I'm going to say it repeatedly today. BPA turns into log base B of A equals P. I'll write it at the top because I see a lot of the head dancing stuff going on. So we're going to be taking bases that have powers that equal something called an argument or the answer. Like we've worked with those 2 to the x, 2 to the third, 4 to the 7th, whatever. Base to a power. And to write it in a logarithmic form is what it's called. We write the word log, like, no joke, the word log, L-O-G. I almost always loop that L just so it doesn't wind up looking like 10G, but that's just me. And then we take that B, the base of our exponent, and it becomes what's called the base of the log. It goes really small, and it goes below the G. Then that argument comes on this side, and it equals the power. These two things mean the exact same thing. They are a way to interchange. And the whole point of a logarithm is it takes our exponent and puts it down in the line of normal numbers. This is what we're going to be practicing today, just switching between these two forms. We're going to play match them up, basically. I need a different. There we go. So we're going to take our base and put it as the base of the logarithm. We're going to take our power and put it over here. We're going to take our argument and we're going to put it here. So we're going to play match them up with BPA log BAP is the way I remember it. BPA log BAP. It's the order we put things in. So what do these look like? If I give you something like this, log base 4 of 64 equals 3. Looks like a whole lot of gibberish. What this means, what we're going to do is we're going to come up and we're going to, that's not a highlighter. We are going to switch between the pieces. We're going to take our log base B of A equals P and put it back as an exponential. So the base is always this kind of little number under here. So when we switch this over to exponential form, that base, log base 4, that becomes the base of the exponential. What the logarithm equals, way over here on the right, this is our power. And it's going to equal this chunk here. 64. That's our argument, is what that's called. So log base 4 of 64 equals 3 means the exact same thing as 4 cubed equals 64. There are reasons it works to write it like this, and that has to do with inverses. But these two pieces mean the exact same thing. This we know so much more about right now, so this is easier to work with right now. But there's times when we really need it to look like this. So that's what we're going to be doing today, is we're just going to be switching them back and forth between the two forms. So on this next one down here, what is our base? What is 3? So we're going to have our 3 becomes the base of the exponent. What is the power going to be? Negative 5. It's this guy right here. Minus 5. And that's going to equal the only piece we have left, which is this piece here. Our 1 over 243. Which, if you type that into your calculator, that does work. 3 to the power of minus 5 is 1 over 243. Last one like this before we start going the other direction. What's our base? 9. What's our power? 1/2. And it's going to equal 3. So these 3 statements, or these 6 statements, all mean the same as their partner within here. The 3 statements I give you are interchangeable. These mean the same thing. They're just in different ways because this is easier for us to do right now, but eventually this is going to be easier to type into the calculator. Okay, let's try going the other direction. Actually, nope, we're going to do it again. Sorry, helps that I pay attention to what I'm doing. One more time, and then we'll go the other direction. So we've got log base 125 of 5 equals 1/3. What is this going to become? When we move it around, I want you to try it. What did you guys get? Yes. 125 to the 1/3 equals 5. Excellent work, guys. So this is switching between the forms. That would be our answer. 125 to the 1/3 equals 5. These two statements mean exactly the same thing. We're just going to need to be able to switch them back and forth for reasons that we haven't gotten to yet. Now we're going to go the other direction. So we're going to write things as logarithms when they've been given to us in an exponential form. And it's the exact same process. The base of the exponential becomes the base of the logarithm. Our power from the exponential is what the logarithm equals. And the equals from the exponential is the argument of the log. So on this first one, we have our base of 7. So this is going to become a log. And again, I always loop that L. That's just a me thing because otherwise it starts to look like 10G. And we're going to do log base 7. So I'm going to put a little 7 down here under the log. When you're writing this on paper, like lined paper, usually I will just like put the 7 under the line like that. So this is lined paper. That's how I would write that 7. It doesn't have to be all the way under. Like I know some people that write their bases like this across the line. But that's the way I typically write it. So log base 7 of our argument. So this guy is going to come next. That's our, oh, that's not a pen. 1, 1, 7, 6, 4, 9. We sure gave you a nice, easy one to write. And what that's going to do is that's going to equal our power, which is this 6. And that should have been purple. There we go. Fix the color. So again, these two statements mean the exact same thing. They're just written in different forms. So we're going to do the same thing down here. We're going to write this as a logarithm. So I'll give myself a line just so that it matches you guys' paper. And we start out by writing the word log. What's our base going to be here? 8. So log base 8 of what's our argument? 1 over 512. And that's going to equal -3. Excellent job. And that's all we're doing with that for right now. We're just switching between them. So our last one, we're going to have log base what? 8 again. Of what's our argument? 4 equals 2/3. Good. Excellent work, guys. So it's just about moving them in between the two places, like just switching them back and forth. All right, write this one as a logarithm. I want you to try it. when we write this as a logarithm, what do we get? Okay, that just starts with log. Log base 2 of 512 equals 9. Boom shakalaka. So what we're going to do next, and this is the last piece for today, is we're going to use these to find an answer. Like we're going to find an answer for a thing. So if I tell you we have log base 2 of 8, I want to know what that equals. So I'm going to put a question mark here. I want to know what this is. Well, if we look at that right now, we go, huh? But if we switch that back into an exponential form, where we have our base of 2, we're trying to figure out what this exponent is, because that's the power, and it equals that argument of 8. 2 to the what is 8? 3. So log base 2 of 8 equals 3. Because we can find out just by switching the forms that this really means 2 cubed equals 8. I don't like this thing up here. There we go. So log base 2 of 8 equals 3. So when we say evaluate, that's exactly what we mean. We want to know what fills in this blank over here. I want to know what my answer is, what my missing piece is. So for the most part, that's going to be our power. So we know that this equals a power of some sort. So let's go find it. So we have log base 3, which means we have the base of an exponential that's 3 to some power that we don't know yet, that we're trying to figure out, equals our argument of 9. What is that power going to be? It's going to be squared. So P is going to equal 2. So I'm just going to write the whole thing out down here just so I don't have to erase stuff. So log base 3 of 9 equals 2. Because it's 3 squared that gives us 9. So we can find these pieces. These are the first kinds of evaluation of these logs that we're going to do. We are going to do 2 more. So we've got log base 5 of 5, and we want to know what it equals. And it's going to equal a power of some sort, because log base b of a equals your power. So we know when we switch it around, we're going to have 5 to some power equaling that argument of 5. What's that power going to be? 1. So log base 5 of 5 equals 1. And that's going to be true whenever your base and your argument are the same thing. Like, that's always going to happen. Log base 5 of 5, log base 7 of 7, log base 2 of 2. They always are going to match. And then our very last one over here, again, we want to figure out what power this is going to equal, what the exponent has to be here. So when we switch it around, we get 7 to some power equals 1. What does that power have to be? 0. The P has to equal 0. When we are switching around the forms like this and trying to find solutions this way, like without having any other tools at our disposal, it's always going to be something we can spot like this. Like, you're not going to have decimally answers unless it's like the 1/2 because that's a square root, because we can do that. But even that might be a little bit much. At this point, it's always going to be something we can spot. Like 5s go to 25 or 125. 7 goes to 49. Like that kind of stuff. It's going to be things that we know. We will eventually get into doing it with stuff where we have weirdo decimally numbers and irrational things and grossness. But for right now, it's always going to be numbers that we've seen before and that we can recognize. Okay, so it really does, for this part, just take practice and to do it over and over again and repeat it over and over again. So, I'm going to give you the first homework for Chapter 8. It has what we're going to do tomorrow and Wednesday on it, because I know it doesn't make super much sense to go straight into it, but what we're actually going to be starting with is graphing these. Since we know these are inverse functions of something we just worked with and just graphed, we are going to graph logarithms based off of the exponential stuff that we just did. So the front side is what we did today. The back side has a couple of graphs that we will work with tomorrow and Wednesday. All right, and you guys have a good almost 10 minutes. You can start working on it. The chapter tests from Friday are graded and in. If you'd like to see it, you can. I gotta get the folder out. But they're done. They're in. They're up on Skyward. They should be. I haven't double checked it, but they should be. They're up on Canvas for sure. Yeah. Let me get it. You guys.